So, welcome everyone to the talk. My name is Álvaro Videla and he's Michael Lane. We are going to do a joint talk about global scaling at the New York Times using RabbitMQ. Anybody from Portland here? Yeah? I went to the game, great crowd. It was really, really fun. So, my name is Álvaro. I work as a developer advocate for Pivotal or RabbitMQ. That means from writing a sharding plugin for Rabbit or doing client work in the sense of maintaining, let's say, the PHP client or coding some stuff for the broker or presenting a talk. There's a lot of things involved in being a developer advocate. So I'm not the marketing guy, let's say. I'm usually programming. I wrote the book for Manning. I made a simulator that I will show you later, and the one that you are using for the challenge for winning a hoodie. And I blog about internals. If you want to learn how RabbitMQ is implemented using Erlang, you can go there, and that's my email, GitHub, and Twitter. So that's the book. I'm co-author together with Jason Williams. He's from the States. So, a bit of background before coming into what is RabbitMQ. I used to work in China for 3 years. We had a dating site for Germany, actually, made in China. You can guess the quality. It was very good quality. And we started using Rabbit at some point because we had to scale the messages between users. And before that, I used to work in an adult content delivery network, let's call it that way, in Latin America. It was pretty big, actually the biggest for Latin America. It was based in Uruguay, where I'm from. So that's a bit of my background. I always been doing queuing things, but now focus on Rabbit. Then I went over the not invented here part of my life, and now I'm using something that is out there. So what is RabbitMQ? RabbitMQ is a multi-protocol messaging server. It's open source under the Mozilla public license. It's polyglot in the sense that you can extend it using languages that run on the Erlang virtual machine, like Erlang, of course, Elixir, probably least flavor Erlang. And you can also connect to Rabbit from many programming languages. It's written in OTP and Erlang, which means all these concurrency, fault tolerance patterns that Erlang is well known for. We support them at RabbitMQ. In the structure, this means less code to write for the RabbitMQ developers, less bugs, basically. So we are using a quite trusted platform for building the broker. It's a multi-protocol. This means you can connect from AMQP, MQTT, and STOMP. AMQP stands for Advanced Message Queuing Protocol. MQTT and STOMP, you can Google about that. MQTT is a protocol. It's used by Facebook, as far as I know, on the iOS chat for connecting to their chat servers, because MQTT is for small devices and low battery resources and intermittent networks and so on. STOMP is made it's like text-based protocol. It's used at the CERN in Switzerland, for example. And at the CERN, they use every product that ends in MQ is probably somewhere in the stack at the CERN, basically. And you can read there why will you want to use one or the other. You can mix them all together and so on. And for the ladies, don't worry, they were giving fake mustaches yesterday. Sorry for the mustache thing there. It's polyglot, since you can connect from Java, Node, Erlang, PHP, Ruby, .NET, Haskell, to name a few. The Java client, the Erlang client, and the .NET one are officially supported by the RabbitMQ team and developed by the RabbitMQ team. The Ruby client is developed by a RabbitMQ developer, but from his open source side, I maintain the PHP client. We also contribute to the Haskell client, and so on. And there is even support for that from the other times, like I was not sure if I was born. You can get Rabbit from there. And just to show you how RabbitMQ works, I will use the RabbitMQ simulator to explain things. So, when you have messaging, what you do is to have a producer and a consumer, and the idea is to get the data from the producer to the consumer. To send data, you need an address. So whenever you send a letter, you need to send it somewhere. In this case, in RabbitMQ, they are called exchanges. So if I send messages, they just die at the exchange. Why? Because I don't have a queue. If I bind a queue to the exchange, and then I send messages, the messages are routed to the queue, and they are queued there. You can see these numbers growing there. So finally, if I plug or subscribe my consumer to the queue, I start receiving messages. If I need to scale, because let's say I'm resizing images and I have too many images, Rabbit will do kind of round robin between the consumers. So you may be wondering, why do I even need an exchange when I just want messages in the queue, right? The idea of the exchange is a router. So you can have more than one queue, send messages, and they will be sent to both queues. But let's say, like in Switzerland, whenever you buy a train ticket at the station, you are greeted by a machine, and you press a button like you want international tickets, let's say, or local tickets for the local train system. So when you arrive there, you want international. So in RabbitMQ here, you specify a routing key, international, and the message is routed there. Then another customer came that wants to buy a local ticket, and it will be sent to the other queue. So basically, like when you are at the airport, you are queued for business class and for the rest of us, let's say. So you can choose which queue you will be on, and then you have the people at the counters are the consumers. So Michael, when he presents about the New York Times use case, will speak a lot about routing and specifically about topic routing, because an exchange is just an algorithm to route messages. That's it. The direct exchange is kind of doing select from queues where routing key equals binding key. The binding key is the one you have here, the routing key, the one you specify on the message. So RabbitMQ is not doing an SQL query because we don't have an SQL backend, but just to give you an idea. And you can see that here it says direct. That's the direct exchange or direct routing algorithm. There is also fan out. That's like a pub sub when you want to do broadcast. And topic is for multicast. So if I change the exchange to be topic, I'll give you a different example. Let's say you have many servers all sending logs to Rabbit, and suddenly you are interested in logs from server 1, application 1, and there are errors. And in this other queue, you care about server 2, application 1, error as well. So if I send a message, server 1, application 1, error, it will go to that queue, and if I specify server 2, it goes to the other queue. So that's kind of a direct exchange, nothing fancy. The point is that you can specify a pattern which is word separated by dots. And let's say you want a queue that doesn't care which server originated the message. So you can have a binding key saying star.application1.error. And then when you send a message, it will go to these two queues, but if I say server 3, it only goes to that one because it has a star. The star matches one word, only one word. It's not like a star in a regular expression. But let's say you want another queue that says, I want to get messages. I don't care which server sends them, as long as it's application 1, and I don't care if there are info, warning, error, and so on, so I can have a star there. I change that, I send the message, but then if I just say info, it only goes to that queue. And finally, this is getting messy, not the Argentinian player, but kinda. And if I say, I only want to listen for errors, so you can use a hash, and you could use star.star.error, but that could get messy with a long pattern, so you can use a hash, change it, and send this one. Won't go there, but if I have error here, it will get there. If I have application 2, it will get there. So that's the advantage that topic routing gives you. You get all these patterns that you can mix and match and then do all this kind of routing. You can say, for example, I care about every log getting into the system. So you can just have a binding key, which is just a hash. So that will go there. If I have blah, it will go there, and so on. So in messaging and in RabbitMQ, what we do is to have a producer of data that sends data to a consumer. Data is sent to an exchange, which is the address. Data has to go to queues, and then the consumer will get data out of the queue. Any questions about this? Yes?
Well, you mentioned that exchange needed to route the message. Regarding the consumers, why don't they have a kind of exchange structure to connect to multiple queues, for instance?
As a consumer, you can connect to multiple queues. So you can subscribe to many queues at the same time. You can bind a queue to many exchanges at the same time. So I can do this, for example. You can have exchange-to-exchange binding to do like subnets, things like that. And there are many options for the routing and how you get the queues. I'm not sure if the simulator particularly supports that use case, but RabbitMQ definitely does. And since you asked the first question, this book is for you, so you can pick it up. And clap, please. Yeah, so to keep going with Rabbit, there are no more questions, sorry, we don't have time. So you lose your chance for that. So that's a simulator. You can see it on GitHub. We have it on the booth. You can win a hoodie with it. It can also export the topology. So whatever you see drawing there, you can export it into Rabbit. You can also import from Rabbit. So you can debug. You can say, why I'm not getting the messages from A to B. You import everything into the simulator. You add a producer, click send with your properties, and you will see why it reached or it didn't reach what it should have. And you can also export the simulator as like in a player mode. So you can write docs and say, this is my topology for image resizing. This one is for whatever. And below you have the drawing with all the things flying around. And I know in Switzerland, banks, for example, they use it to teach the new hires how RabbitMQ works. So from my point of view, that's quite cool. So what do you get out of the box with Rabbit? This is my final section before we go to Michael. So Rabbit has no message loss for some definition of no message loss. It has persistent messages. That means when you publish the message, you can say it's persistent or not. You can have queues that survive broker restart. So if you combine those, then the messages shouldn't be lost. We have replication in the data center. So that's if your server catches fire, it should survive in the other node. We have publisher confirms. There. Yeah, so of course, as any software product, RabbitMQ needs to f-sync. It needs to f-sync to the hard drive to actually persist the data. There is no magic, right? So if you use publisher confirms, RabbitMQ will send you an ACK back to your producer when it has sent the f-sync. So if you really, really, really want to know that the message is there, that's the way to do it. And if you have a cluster, let's say from 5 nodes, 3 of them must replicate the data, then when the 3 have the data, Rabbit will send you the confirm. So we have message acknowledgement. So a consumer can be in ACK mode or not, and if it's in ACK mode, it can send a Rabbit, yeah, I resized the image, you can delete the message. We have mirror queues, as I said, to replicate data in a cluster. It supports message ordering. There is a myth somewhere that RabbitMQ doesn't support message ordering. Yes, it's been there since the beginning. The queues are queues, first in, first out, basically. We have dead letter exchanges. So if for some reason your message cannot be processed, you can send it to an exchange, dead letter, and process the message later. Like if you reject a poison message, for example. We have alternate exchanges, like if you saw at the beginning, when there was no queue, the messages were dying at the exchange. We can have an alternate exchange. So you can tell Rabbit, if this exchange cannot route the message anywhere, at least put it in the alternate exchange. And I see later why it's getting there. We have message and queue TTL, so you can specify time to leaves on the queues and the message to prevent unbound buffers. So for some reason your consumers cannot keep up or they are offline or whatever, you can do that to just expire messages. You can have consumer priorities. Let's say you have an heterogeneous cluster. Let's say one machine with more CPU than the other. So you want that the one with more CPU catches the resized image, more messages than the one with less CPU, for example. So you can prioritize consumers. We have federation, which is a way to replicate across data center. And we have shovel, which is another way of replication that Michael will talk to you now. So thank you, and I go to Michael now. So if you have questions, you can get me later, basically. So.
This is my 50th year in computing. I remember the introduction of the IBM 360. It was all pre-internet, so it's lost from memory, totally. But I went to lectures in rooms like this with Edgar Dijkstra, which some of you may know. And at that time, we were really focused on structured programming and what is that. But it's been a great ride. The Fabric is kind of an invention, and I have to say it's sort of my invention. We're trying to reinvent and re-architect how we would deliver the news, how we would gather events from users, how we would connect everything and do it with a messaging paradigm. And so we started with this. We knew we wanted to be flat. We wanted to be mesh connected. We wanted the mesh to be auto-healing. We knew we would spread lots of different kinds of nodes out across this mesh. And preferably we'd keep them all small and keep it all easy to manage and easy to deploy. I was originally brought into the New York Times to work on cloud infrastructure, and so I was familiar with that and familiar with some of the opportunities that are in the cloud, and they're big opportunities. But really the idea was just to connect everything together. So it's kind of if devices are the proxies for users, then this is kind of the Internet of Things. And how could we look toward getting news to appear on your toaster when there's breaking news, and so on and so forth. So we spread our nodes in the mesh across the regions of Amazon. And we do this because we want to keep some independence between the pieces. And we do it for least latency so that we can move our information in the form of messages close to where our consumers are. And of course, we spread across the zones in Amazon as well. And so we can operate in up to 20 zones around the world. So I'll spend a little time on this class, or on this slide. We've got millions of users. It goes up and down. We can have, our user population can grow and shrink on a normal day by an order of magnitude. On a big news day, it can be 2 orders of magnitude. So we have a big cycle of users. So all of our user-facing elements, which we'll talk about later or see later, the gateways, are auto-scale. We provide different classes of service, and if you think about it, anything news that's generated by New York Times, when I first went there, they said, wow, we generate, the equivalent of a Harry Potter novel a week. And I thought, oh my God, we've got to run a $3 billion business off one Harry Potter novel a week. That's not very much information, but it's very high value information. And so that's our gold information. So what we do, and this is more typically found in things like Cassandra and so forth, which we use, by the way, which is we replicate our messages, so our important stuff. So when stuff comes in that's important, when we had 3 breaking news items this morning so far about Affordable Health Care Act and about flights to Tel Aviv. When they come in, we send them everywhere. We process them in parallel, just in case some part of our infrastructure is slow or has gone down. And they race to get to our consumers of information. In the process, we resolve those messages. But everywhere, we can handle duplicate messages. Okay. Silver messages, we prioritize them. So that would be a more typically individually addressed message that might be important. Bronze messages are queuable messages. That's like one of our internal services might drop 1.5 million messages on us that are for users, inviting them to participate in a particular thing. And we might spread that out over several hours. So we'll queue it behind the other things. We're message-based. We took the promise of WebSocket a couple of years ago. And WebSocket, I think, is actually slightly inappropriately named because it's a messaging protocol. It's not really like a socket. I mean, it's a messaging protocol. It's got framing, got all this stuff. So it's really for messaging. AMQP, which is what RabbitMQ runs. And we, as a bridge protocol, we use SockJS also, which will use all of the other kinds of messaging protocols you can run over HTTP. But we use that to connect everything. I've touched on it. We're idempotent, replicate, racy, resolve. Everything is event-driven. In fact, I was looking at this today and I was thinking, I've kind of forgotten how to do procedural code. But we use libev heavily in C, in Python, and in RabbitMQ. Our interface uses libev, and our gateway uses libev as well for WebSocket. So how do you deal with them? When in doubt, you resend. So our producers, that's what they do. I don't think the message got through. First thing they do is resend. Then we track, okay? Because we can handle duplicates. If they send a duplicate, it's okay. If you lose your connection, reconnect, reread, and talk about a mesh with a memory. The memory is there because, of course, people are not connected all the time. Yet when they do connect, they want to find what they missed. And that's what we provide. Oh, great. Thank you. Let's try that again. Remind me later. Thank you. Much later, preferably. Okay. So what's a message? And I'm not going to belabor this, but we use the envelope for routing and for locating when a message is at rest. Really all the stuff of interest to us, because we're a service to the other people in the New York Times, is in the metadata. When everybody says, well, why did that happen? It's, well, the metadata made us do it. I'm sorry, you provide the metadata, we use it. And so we derive envelope data from the metadata. And the body we don't care about, it's either there or not, but it's opaque as far as we're concerned. We deliver what our users want. So we've got these various technologies, RabbitMQ, WebSocket, and we basically take the envelope, the metadata of the body, and we represent those in those different technologies. So the envelope gives us the routing key for RabbitMQ. WebSocket really doesn't have the concept of routing. You're really just on a connection. When we're working with S3, we store messages by UUID, which we derive from metadata. Cassandra, we use something called the path, and I'll talk more about that. Routing key and path are related. Metadata, in general, you can kind of think of it as JSON. So what happens? So if we publish a message, it goes into our core, the core of the fabric, through a gateway to a device that goes to a user. If the body is big. That's the only thing we look at is the size of the body. Early in the process, we'll store that in S3. That's the only synchronous activity we have because we have to wait for S3 to come back and say it's got it. And then we'll forward a reference. We'll put a reference in the metadata. And from then on, the processing happens. So our messages in general are small, on the order of 2K. At the same time, everything else there is asynchronous. So at the same time we're broadcasting that, sending that message to the user, which might be individually addressed, or it might be a broadcast message like breaking news. We're also storing it in Cassandra. Different protocols are shown there. Now, a subscribe just kind of works the other way. The user initiates a subscribe, and it's really a subscribe and a login are very closely related to us, for us. When somebody subscribes, in effect, we give them what they've missed. Okay, to get that, we go look in Cassandra. Maybe there's something there. That's why it's a dash line. Maybe there's a reference in that metadata that comes from Cassandra to an object in S3 or CloudFront. So we'll marry that up in the device and show it to the user. These things happen very fast, by the way. This is kind of more interesting one and leads us in an interesting direction. So a user decides to dismiss a breaking news notification. We want it to dismiss from all their devices. So they might be logged into a browser, have their iPad, iPhone. They may or may not be connected with any of those devices. So what we do is when they dismiss, then we'll bring it through the gateway, record it in Cassandra in case for devices that are not currently connected, okay? Cassandra does its own propagation of that through the cluster, through its cluster. And then the core handles switching this around in case there are other devices connected through other gateways, possibly in other regions. So for example, from New York, least latency might take us to Dublin sometimes, and it might take us to Oregon other times. So we want to, if somebody's on a device in both regions, we need to get to them. And that's how that works. So you can see how chat would work, and we're headed toward things like that. Chat, special chat, meaning if somebody's focused on an article and they're commenting, maybe there's a group of people that they're associated with who can see those comments, and that an article in the New York Times becomes a center of a conversation. So the only difficulty, those were pretty simple diagrams before, but they're actually lots and lots of replicated components. Pretty much, though, all the connectivity of everything except the core is pretty simple. The core can be thought of as big switch. Cassandra takes care of itself in terms of its replication. The gateways are each connected to one or just a couple cores. The CloudFront and S3 boxes are well known, so they don't move around. We can handle millions of messages. We can handle millions of devices. They all connect to the gateway, and millions of users. So now we're going to get into some of the routing part, and this will really be the focus of the presentation here. So we need to route the message to the user, and we need to find messages for the user. We also need to route messages internally. So we basically have two kinds of routing, both of which are derived from the metadata. This is getting into the TLDR part of the talk, so if you nod off, it's okay. Path elements are text. This is the Rabbit. We give the path elements certain names. The first one's really important. So here's a breaking news item, for example, a path. This is how we're going to route it to users. And you join it by a period. That's RabbitMQ for you, okay? But for persisting that message, we use that same path, but it indicates in Cassandra a folder. And by the way, we used to use DynamoDB. We've used React. We kind of front end the NoSQL guy, and it's basically pluggable in our system. And we store everything there, in effect, in timestamp order, reverse timestamp order, using the UUIDs. I won't bother to read the UUIDs. Is that okay? To subscribe to a path, you bind, typically using wildcards. And he's already covered how you do this, but if you want all the breaking news messages, you'd use the hash. And you can retrieve from persistent storage also by the path. Okay, so you can get all the breaking news messages with this path, in effect the folder. But you can also use the wildcards. And this will give you all of them, all the current breaking news items. Basically, and I can't go into this now, but the Cassandra Data Store will give you a subtree under this tree. Okay, so I have a tree consisting of feeds, breaking news, there are other things at that level, and then a whole bunch of other stuff, and that can go to any number of levels. The Cassandra Data Store will give it, with a single request, will give you the responses. Our internal times for those are under a millisecond. So the key thing here is, I think we'll kind of skip through. You can use the same paths. So this simplifies our logic internally. And we're using the same paths for routing and retrieval for these messages. We have to treat individuals a little differently, and that is because the namespace of individuals gets too large the way we have it. And the way we do that is basically to break that up and take advantage of try-search in order to very efficiently do this. By doing this, we can, in effect, almost every one of the core nodes knows who's subscribed. The rabbits take care of routing this information around for us, and each one of them knows. So if something shows up for a particular user that's logged in, it will get routed directly to that user. That's path addressing. Now we'll talk about the internal addressing, which we call the post office. And it's a logical bus connecting all the services. It's physically segmented. We connect it with federation. Alvaro talked about that a little before, federation and shovels. Actually, we use a mix of shovels and federation, but we're moving toward federation, which kind of automatically connects all of our instances in the core. Each address, every service we're running has got these three unique elements, uniquifying, I should say, which is not actually a word, and some additional qualifiers. And we use those attributes to create addresses. So we create a from address, for example, like this. So any instance or application invocation that's sending something knows what its address is and picks that up and sets it. And there's to address. It's basically I'm routing to something. I might be routing to a specific instance, or I might not care. I might be just routing to a service, and this shows routing to a service and an action. So if I were to put those together, we can construct a routing key like this. And here's an example where I've broken the pieces. So that's basically a message asking for a route action, and it's addressed to any service that will perform that in the region. Okay, so that gives you a sense of how we do this. The services bind with typically wildcards. So they're first of all going to bind with their own address to get anything specifically that's headed for them, but they're also going to bind based on the services. And they can provide multiple bindings, so they can offer multiple services. And this allows us to really focus our services and have them loosely connected. So we have a whole bunch of loosely coupled services. We can rewrite them. We can do them in Go instead of Python. We can do them in Node.js, which we've used as well. And they don't care because the Rabbit doesn't care, and we're just using the Rabbit, and we can use the appropriate connection. Okay, so we do this with some common methods that we have in the fabric. So what kind of routing do we do in the core? For load balancing, we'll do this kind of thing, and Alvaro showed this. So a message comes in, and we'll either send it to one core or another. There can be many of these cores, by the way. The cores can actually balance their queues by federating the queues so that we don't overwhelm any portion of it, and if any piece goes down, other parts will automatically pick up. For replication, the OR becomes an AND. And for distribution, there may be more complex routing in the core. In other words, all the core elements will shift stuff around by themselves, in order to get it to the right devices. But there's some problems with that kind of our current implementation, which we're moving to address. It actually works really well, but there's some things we'd prefer the core instances to be less complex. Right now, they're federated with each other, so there's an n-1 problem because we fully map. And they're clustered, so that just adds the complexity. I mean, it's great because we can cluster across zones. If a zone goes down, the cluster keeps going. Everybody shifts automatically, but it adds to the complexity. They're also running all the services, which, although they're small, there are a collection of them, and that adds to the complexity and making them, of the elements that we have, more of a problem to manage. But this is particularly the problem, is that they're difficult to auto-scale because they're a little more complex than we can use auto-scaling for. So where we're headed is kind of factoring out this connection portion and routing piece into a Rabbit router. And this is an old technique, buses have turned, bus routing's turned into star routing before now. And so the new core will focus on services. Everything will connect to the Rabbit router, and the bus becomes a star. Okay, there's a lot of stuff I didn't cover about the fabric. The different parts of the fabric, auto-discover. We use Surf for that. It's Golang based. We use Ansible to manage our deployments. We continue to simplify things, to factor them out, to make them small, to make them auto-scale. We've had a few war stories. I was telling Alvaro, things have gotten so reliable that we have two big problems. Really, it's one problem. Human error is our problem now. And we had inadvertently, one of our people terminated all the instances in a region once. And of course we noticed, but everything shifted to the other region automatically because of the least latency routing and so on. All the users reconnected, all the producers were redirected. So the good news is that nobody else noticed. And we had a similar situation with poison messages. But because things are asynchronous and there are backup ways for doing things, the poison message could be isolated, and we could shut off that stream by switching a binding. And again, nobody noticed. It was a little slower than usual, meaning that it was 300 milliseconds to log in instead of 200. So all in all, the fabrics worked out pretty well for us, and that's it. If you've got any questions, I don't know if we have any time. We're out of time. Okay, we're out of time. But you can grab me. I'm the guy in the purple shirt.